Today, we're very happy to have Jackie Faherty. Jackie got her PhD at Stony Brook, and then was at Chile. She was a Hubble Fellow at Carnegie, and then came back to the area at the American Museum of Natural History, where she is now a senior scientist. And she's going to tell us about brown dwarfs.
Yes, great introduction. Hi, everybody. I'll try and talk into the microphone so that anybody on Zoom can hear me too. Hopefully you can hear me on Zoom.
Yeah, and they're ceiling mics too, so it's not
okay,
terrible
so it's not
on Zoom if you don't hit the mic.
All right, cool. I'm controlling the talk on my phone, which is why I'm going to hold it in my hand. I'm not trying to be rude. And that's point one. Also, this is a small audience. I hear you guys interrupt a lot. Please do. I'm talking about a topic that I also realize is not the favorite go-to for everybody necessarily, but I'm hoping I can convince you by the end that you should care about these objects called brown dwarfs. And if you end up serving on a time allocation committee, possibly for the James Webb Space Telescope maybe, you'll realize why you should give all of the time to these objects. That's okay. Part of my goal in giving colloquiums to convince you. Also, at the very end of this talk, I'm going to show you fresh off of the telescope from JWST Data. So pay attention now, of course, but at the very end, you're also going to see some like brand new data, cutting edge, totally new chemistry. Can't believe we have it. Exciting, exciting. All right. So the topic of today are brown dwarfs. They're these objects that are in between stars and planets. They literally bridge stars and planets. So in the 1950s, it was theorized that you could get the collapse of a molecular cloud, it formed stars, we knew stars came in different sizes, but then it was theorized like, okay, well, you're gonna get to a mass whereby you're not gonna be able to get the core hot enough to get nuclear burning going. And thus was born the idea of degenerate objects where electron degeneracy pressure essentially is kicking in before you can squish the material tight enough in order to get the core hot enough. And these objects just simply cool throughout their lives. So unlike stars that have a main sequence where you can sit there for 7 billion years, 10 billion years, and basically hold a constant temperature and look a similar way, creating a main sequence, that is not the case for brown dwarfs. They are born at a temperature. They have a little bit of deuterium burning when they're first born, but then they just cool off through their lives, morphing from looking like a star, not like the sun, but a much lower mass star, but a star just the same, to looking like Jupiter or lower temperature, things you haven't even thought of yet. Because every brown dwarf that was ever born is still around. They don't go anywhere. They don't die in the stellar term.
If they don't burn no hydrogen, why do they look like a star? Just residual heat?
So when they're born, they're pretty hot from gravitational collapse. And they have deuterium burning at the beginning. And so when I say they look like a star, they look like a low mass star. So they're not going to look like the sun. They're going to look like an M-type star, which is got some rich, different kinds of chemistry. If you're not used to looking at them, they have a lot of molecular features, for instance, in their spectra. The brown dwarfs will look like that when they're very young. All right, they come in a couple of classes, speaking of which, there's your brown dwarfs. And the classes that they come in span effective temperatures from about 3,000 degrees Kelvin all the way down, and I'm going to say this twice, all the way down to 250 degrees Kelvin. That's the coldest compact source we've ever discovered.
And how hot is Jupiter?
250, 125. So it's about 125 degrees Kelvin warmer than Jupiter, isolated outside of our solar system. My argument is that if you want to do comparative planetology, if you want to go ahead and look at objects and take the atmosphere of this thing or take the image of this thing and compare directly to what's in our solar system so we can truly see the diversity of worlds, these are the objects. You don't have to block the light of a star in order to access their light. They're isolated for the most part. And you can study them and you can see the fantastically intriguing chemistry that drives giant planets. And I'll show you some of those by the end because I have JWST data on a bunch of objects that no one's ever seen before. The other important thing here is that mass is age dependent. And this is why they're a little bit of a mysterious class of objects. Because you can find an object that spans a temperature between 3,000 and 250 degrees Kelvin, but if you don't know the age of how old it is, you actually have no idea what you're studying. You could be studying a low mass star, you could be studying an object that's in between stars and planets, the brown dwarf, or you could be studying a planet, a 5 Jupiter mass object, a 30 Jupiter mass object, and an 80 Jupiter mass object can look identical at different stages in their morphing if they're degenerate like these objects are.
So meaning that if I see something at a certain temperature, the mass that I infer depends on the age that I think it has.
Yeah,
That's what you mean? It's
mean,
not that the mass changes with age.
Right, no, that's right. What it means is that you can't just find an object and measure its temperature and then say that's a 25 Jupiter mass object. Because you don't know if it's just really young and it still has all this internal gravitational collapse heat or some deuterium burning.
But this is just because you don't know the distance, right?
No, you know the distance.
But if you know the distance and then you know total luminosity, is it really that degenerate?
Yeah, totally degenerate. It doesn't
So
matter.
it will have the same radius and the same temperature with different masses?
The radius will be different, but at this point, we have no way of measuring radius.
But you do measure, if you know the distance, then you measure luminosity, then you
do.
temperature, then you
That's
measure
right.
radius, no?
No, because to get to the so you get the luminosity. There's a couple of choices here. You get to the luminosity. If you have the parallax, you get a beautiful spectral energy distribution. Integrate under that, get the bolometric luminosity. The next stage to get to the effective temperature is to know the radius. So you have to make an assumption about the radius in order to get.
But don't you see the spectrum and therefore the temperature?
Spectrum doesn't tell you, and the spectrum gives you a class, but it's not telling you the effective temperature of the object. So
I'll catch you after the talk.
yeah, this is
in
subtle
detail,
and complicated, but I actually have made half my career out of showing why that it doesn't work. Because the way gravity ends up playing. Okay.
But is that because the spectra really don't have temperature dependent features, or because the relationship between the spectrum and the temperature is not understood?
The relationship between the temperature, the age, and the spectra are very hard to disentangle.
I see.
So that you cannot easily tell the difference between an object that's very young at this temperature and an object that's very old. And it's become very clear that young objects of the same temperature get misclassified as a warm, they go the opposite way. You will misclassify them as a cooler object because of what pressure broadening and gravity ends up doing to the spectra. So spectra are not a great measurement of
They are not
temperature.
black bodies?
No, definitly not black bodies.
Okay.
Completely, you'll see, I'll show you spectra, they're terrible. Love them, but they're terrible. All right, there's a couple things I want to get to. This is a little rendering of movies of brown dwarfs found in the field. I'm going to do a quick promotion as a sidebar on this talk. All of these movies here, these are time frames. I don't know what I'm doing here. There's from the Wide Field Infrared Survey Explorer, all of these are dancing orange dots. These are discoveries that are made from a citizen science project that I co-founded and co-run. It's called Backyard Worlds, Planet 9. I'm not actually trying to find Planet 9, different story. But a citizen scientist named Dan Castleton developed this really awesome piece of software that I would love to encourage you to look at if anybody in here cares to look at infrared time-based images. It's called WiseView, and we're basically blinking between maybe 6 years of data, and you can see the stars, stars, whatever the heck, I don't know, whatever these things are. All of this, probably just stars, background stars, and then these orange dots are dancing. They're orange because they give off the majority of their light at 4.5 microns in the mid-infrared, because all of these are pretty cold objects. This was all just to show you, like, a lot of them are found isolated, yeah.
So are these
One, are these all different brown dwarfs? And two, what are the letters at the bottom?
Yeah, so these are all different brown dwarfs. 1, 2, 3, 4, 5, 6 different discoveries. And the letters are telling you the spectral type of the object. So on that former slide, I just had showed you how the objects, I guess it's not gonna work, how there's different classes of objects, and they go, M is the warmest, L is cooler, T is a little bit cooler than that, and then Y dwarfs are the coldest of all of them. So this is also to showcase to you how many cold objects we've discovered.
And roughly how far away will you expect these are?
All of these discoveries, because they're so cold, all of these are within 20 parsecs, and the majority are within 10 parsecs. We basically study the objects that are spitting distance away, like we kind of have to, because you can't get to their light otherwise.
And they're moving fast in these images just because from an apparent perspective, they're just closer.
Yeah, exactly.
So it really is just, this is just what you might call reduced proper motion or whatever.
Well, this is just proper motion.
Yeah, it's proper motion.
So this is just showing you the proper motion, and they are all high proper motion objects, not because they have a high velocity. They're all close with a large proper motion, which means that you can really sense their motion within the galaxy.
Cool.
That's the only way we can find these easily as well. But I want to switch to this question, this open question about brown dwarfs, which is how they formed. Because this becomes the distinguishing factor between my planet colleagues, who I adore, my star colleagues, also adore, and then us, that sits in between. We are literally in between the stars and the planets people. And so you ask, what are you? Are you a star or are you a planet? We bridge. But one thing to argue is like, yeah, but sometimes you find some of these things and you're basically looking at a planet. I mean, they are so planet-like. And that becomes wording that you end up using in proposals or in grants or in press releases, blah, blah, blah. All of that gets involved in this. But the question, like, are they planets or are they stars? What would you use to differentiate? The thing we use to differentiate, some people use mass, which is I will just say to you out loud, I think it's a terrible way to define it because it doesn't tell you enough information. At 75 times the mass of Jupiter, you do lose nuclear burning, and so it becomes a degenerate object, so that's a good category. But at the low mass end, at 13 times the mass of Jupiter, you can no longer have stable hydrogen burning, instead you get deuterium burning, but that doesn't mean that you become a planet. That does not mean that. What you want to know is what's the basement of the mass function? What's the basement of the end of the star formation process or the height of the planet formation process? One way to look into that is to look at companions, objects that are co-moving with a star. So while brown dwarfs for the most part are isolated and they're found by themselves, you do get a small number that are widely separated and fully resolved from a higher mass star. So for instance, here's a bright star, and you can see dancing with it is that little orange dot. This is my favorite one. I can tell you a whole different story about this one. This is a really exciting object. This is a K0, almost solar type star, and lost in the diffraction spike of this is this jumping dot. This thing is actually debatable whether it's a planet or a brown dwarf. I just call it a world. So you see them dancing everywhere. So you want to be able to say, like, well, how did they form? Did they form in a disk around those stars? They're really widely separated. These aren't like 10, 20, 30 AU. These are hundreds of AU away or thousands of AU away, thousands of astronomical units, very far on a solar system scale.
Sorry, you said debatable brown dwarf or a star, as if there is a unique definition of a brown dwarf on a planet. Is there a definition, because you're saying it's important to not misclassify, but in order to not misclassify, you need to define.
Yeah, exactly. This is what I'm going to try and do for you. And I'm going to try and do it using chemistry. Chemistry and then these companion systems. We do not, I mean, the big punchline is we do not have a definition for planet. That's a good definition. We do not. There's no way anyone could stand and say, I can tell you that I know I've found a planet. Pluto is a problem on the low mass side. Fine, whatever, that's for the second graders and everybody on that side, right? But on the high mass end, that's when I come in and my teams, and we cause problems because we find things that are massive, that orbit stars, that look like they could be in the right mass ratio scenario.
But you seem to say anything which orbits a star is a, no?
No,
Okay,
because
I
you
go
get binary
to the-
stars and you can get brown dwarfs that orbit stars. So one way you want to do this is you want to measure the chemistry. You want to measure the chemistry of a host star, and you want to compare it to the chemistry in your companion. Now, we'll just tell you, measuring the composition, the chemical composition of a companion is stinking hard. But I'm going to show you how we've been doing it. And this argument is a very famous plot. We had Karen Oberg give the Big Apple colloquium, I don't remember, 2 years ago. It was during COVID.
Yeah,
1
2020,
year.
I feel like.
Okay, so anybody that might have been there might remember Karen Oberg's team is definitionally measuring disk chemistry. And so what happens if you measure the chemistry of a host star and you look at disks, what you would see is that if you walk yourself away from a disk, you see a specific chemical signature of ice lines. So water will freeze out at a certain distance away from the star. So the host star is here, you walk away, you get a water, the H2O freeze line. You get a CO2 freeze line farther out, CO a little bit further out. And this is all to say what ends up happening is that this is the solar C to O ratio. This is if you look at your star and you measure what the carbon to oxygen ratio is of the host star. The accepted value is like 0.6 or so. The argument, which I'm going to tell you is a bad argument, the argument is that if you can measure the C to O ratio of your companion and find that it's enhanced, it means that it formed in a disk farther away from the star. Because as you walk yourself out, you can see the C to O ratio for these objects that formed farther out in the disk end up being larger because of how you freeze out part of the chemistry, enhancing the ratio. So high C to O ratio ends up telling you, oh, that's it. And you go to a lot of exoplanet talks, a lot of brown dwarf talks, people make that sound like it's the smoking gun. We're gonna measure the C to O ratio. We're gonna measure it and we're gonna be able to say it formed like a planet, it formed in a disk. We figured out what the bottom of the mass function is for stars and the top of the mass function is for planets.
So the argument is, though, that if it had formed on its own, it would have been at that dotted line, just
Solar.
like its other, just like its companion.
Yeah, exactly.
Okay.
So that if you can measure the chemistry, you're able to do a comparison. Is the C to O ratio more like the star, or is the C to O ratio enhanced, indicating that it formed in a disk?
And I'm being an idiot,
Go.
but why does it do this? Is it because what freezes out has a different C to O ratio than what remains in the gas phase?
So in this case, the oxygen gets frozen
because
out.
you're pulling out oxygen.
Yeah, and in this case, C goes, but so do
but
two
two
O.
O's, I see,
Yeah.
got it. So it changes the gas phase. Got it.
Exactly.
Good, understood.
Driving the C to O ratio up. I'll just say, this is a notorious thing you hear all the time. C to O ratio, C to O ratio,
But if
holy
you
grail,
form a
holy grail.
planet there, won't you form it from both the grains and the gas?
You're, I don't
There's
know
an
what,
assumption about what the planet formed out of.
yeah. I mean, the model that exists for this, because that plot had both gas and grains on it.
Right,
So it was trying to demonstrate for you how much you pull from each.
I see, yeah.
So there is a balance that's drawn in that model that's a combination of both.
Okay, got it.
All right, the next plot that you have to get into before I'm going to show you a whole bunch of results is this plot. This is another plot that's like epic in the exoplanet field. Many people use this as their like intro slides. I've produced, mostly you see the plot zoomed in, and the color on this is bad, but it's fine. On the x-axis is the separation of a system, so like walking out in the disk. Well, if it's a disk, you're either walking out in the disk or you walked right on out of the solar system. And so I've placed here where the Earth is, Saturn, Pluto, or Cloud, for instance. This is showing you so you can do a little bit of comparison. And then real far, you can get things that are super far. This is all in astronomical units here. So like we're here, Saturn's here, blah, blah, blah. And then the other thing that you plot up is the mass ratio. You have a big star and a little thing. So this corner down here is telling you something is super tight and the companion's like real small compared to the host star. As opposed to this corner over here, the thing's really far away and it's almost the same mass. And so I plotted on this the entirety of the exoplanet archive. This is every exoplanet that's known. And then all these star systems, these are binary stars basically up here. I pulled this from Gaia Discoveries, from spectroscopic binary catalogs, anything I could find that was a companion just to get the full breadth of all the kinds of companions. And what became clear is that you see there's a couple of, the argument would be, is that if you're in this part of the diagram, you're an exoplanet, everybody would be happy to define that as an exoplanet. So low mass ratio, really tiny mass ratio here, really tight up on it. In theory, all of these should have C to O ratios that are super enhanced unless something whacked out happened. And then up here in this far right corner, you're looking at stellar binaries. So these are a star and a star. No one's arguing anybody formed. There's no planet argument up there. It's just, those are the stellar binaries. But there is a transition area here where I've made a lot of discoveries, as have the direct imaging planet community. But a couple of these I've worked hard to find. There's not many of them, and it's considered a transition area. We don't have a good argument for what the formation, which way does it go? Is it more like these guys, or is it more like these guys? There's observational bias in here, clearly, but you want to measure the chemistry of everything in this transition area and check.
Talking about observational bias, if you go to the separations like 1 AU and you just go up,
Here,
there's
here.
a gap around 10 to the minus 1, 10 to the minus 1.5 in mass ratio.
Yeah.
Is there any chance that that gap is purely observational, or is that really a physical? There really does seem to be a dearth of objects with a factor of 30 ratio to the primary.
I think that this gap,
Yeah.
I'm not totally positive about, because I may not have pulled every single catalog I could have.
Mm-hmm.
And it's also, they don't, you know, like my interest was in the farther off systems
Right, yeah.
here, so I didn't work hard enough to get to these. I worked really hard to find anything anyone had ever discovered that was
Right.
wider than, you know, in the widely separated, fully resolved arena.
Because that
I doubt this is real. This is
But if
probably a
but
bias.
if it's not real, there should be tons of things in the Kepler catalog because there should be eclipsing binaries
Yeah,
in that
yeah.
region, and I do think the eclipsing binaries in Kepler have received less attention than
Yeah.
they should have.
You're right. You're right.
So
yeah.
anyway, I keep saying anyway. I'm saying now to the room.
You mean like the Kepler people who looked at all those light curves just didn't put them in the exoplanet
They tend to go,
archive?
oh, it's just an eclipsing binary.
I see.
When in fact they might be incredibly important objects. I'm kind of saying that backwards towards the graduate students because I'm ready to work on that.
I mean, so what I think would be what an amazing project would be, and this is one that I have proposed to people, is to do all this entire plot, measure the chemistry of both the primary and the secondary, do a really solid job. Do the carbon, the oxygen. I'll argue why you should do magnesium and silicate as well. Look at everything and see what the distribution is across this plot. That would help us understand for real if there is any. Do you start seeing the gradient come down where you'll see some interesting chemical signatures? Apogee and Galah are two surveys that sometimes we turn to see if there's even any way that we could like go after these guys up here and see if stellar twins are truly stellar twins. Like, do you really get the same? They come from the same natal environment. All right, now let me tell you what I'm going to take you through. So, is it even possible to measure the chemistry of the companion? Because that should be something you immediately said, like, well, how are you going to do that? That sounds really hard. Like, we can do it for stars, kind of. We do a good job of measuring the chemistry, but it's hard work. It's really hard work. And so now I'm going to show you answers to these questions. Can we assess the bulk chemistry of brown dwarfs? And I'm going to specifically talk about brown dwarf companions. And then can that bulk chemistry differentiate a formation pathway? And I'm going to start with an object on this plot, which is up here. So it's in like the transition area. It's not, I mean, not quite. It's like the bottom end up here. But this is also special because it was the very first brown dwarf ever discovered. It recently had a dynamical mass measurement measured, and it's very heavy. It's a 72 Jupiter mass object, which puts it right on the border of a star, and it's very confusing because it's a cold object. So here's a spectrum. This is why it's not a black body. This is a spectrum of a brown dwarf. This is wavelength on the x-axis here, and this is flux on the y-axis here. And it's a zoo for the molecules that exist in the atmosphere of this object. I mean, this is low resolution data. So basically you're seeing water absorption, massive methane absorption, and CO absorption in here. This is all the work of my fourth year graduate student, Emily Calamari. And what we wanted to do with this system is see if we could measure the chemistry in the companion, compare it to the host star, and make a definitive claim about how it formed. It's really big. It's 72 Jupiter masses. No part of us believed that it was going to turn out to be formed in a disk around the host star, but we were going to dig into it nonetheless. And yeah, go ahead.
Following up on Andre's question, is it possible that one understands the absorption spectrum so well that you could model it? I'm so ignorant about this
No, it's okay.
chemistry.
Yeah.
That you could model it as a black body with absorption, and those are the complex, well understood absorption depths.
Well, so the next stage of this talk is how I'm going to tell you how I modeled it. And we can't just treat it like a black body. You actually have to turn to a method that's called the spectral inversion technique, or what we call retrievals. And in that, there's really two approaches people take to try modeling brown dwarf spectra. Number one is that you say, I know the physics and the chemistry really well that's going to drive this object. I'm going to input it into a code that I've written. Radiative transfer is really done well. I'm able to figure out, I know the chemistry for an object that I think is in this regime. And then you pump out a grid of models. And then you show up with your spectrum and you say, okay, I'm going to compare to that grid, and I'm going to see what mine looks closest to. But it's bad. It never turns out right. It's always not fitting the data. So that's called forward modeling. This approach is the opposite of that. You say, here's my data. I think I know the physics and the chemistry. I'm going to tell it what I think are the gases involved in this. And then I'm going to let the model try and fit my data. And when you do that, this is a different approach because you're able to play with a temperature pressure profile, which is not locked in then. When you go to the grid models, it's locked in. You can't play with that. So you're not sure how you're going to change, like where something might exist in the atmosphere, where the radiative layer is. All of that is like locked in. But it's also very flexible. And that means that you can fit some weird physics and weird things to these objects. So you have to kind of be careful when you do this approach. I have a team that I've assembled of people that are very good at this. We call ourselves the retrievals crew. My former student Eileen Gonzalez is a part of it. She's now 51 Peg B fellow. She's written a couple of papers on this. Ben Birmingham is the one that's written the code that we use. And then special to this whole project is Shannon Vischer and Marina Gemma, because Marina is a meteoriticist and a cosmochemist, and Shannon is a chemist. And the reason we need them is because you can very easily put a cloud or some condensate to help fit some portion of your spectrum that makes absolutely no sense. We did go through this. We found rust clouds that we got very excited about, hematite clouds, and we thought, oh, they solve a lot. And then we realized there's no stinking way you could have a hematite cloud in an oxygen depleted environment like these objects. That was
Which
taken
cloud, sorry?
hematite.
What does it mean, hematite?
It's like it's iron. It's rust.
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 And you also had a quartz cloud on the
Oh yeah, but those are really there.
Those are real.
I'll show you why those are there. Yeah. No, those are real. That's fine. Everybody knows the quartz. Quartz is fine. Quartz is fine. All right, so here's what the data end up looking like when we model them. So the black is the data, and I didn't actually show you the plot that showed the forward models, but the forward models cannot fit the peaks, and that was fine. Everybody was okay with that. But you can see the retrieval. We can kind of nail it. You can really get to a lot of the features like really well.
Sorry, so you are fantasizing various clouds in order to fit what you see. Is it more or less the strategy?
We throw in some clouds. We say, let's test out a quartz cloud, an enstatite cloud, a forsterite cloud, and let's see if using that cloud is a better fit. Zinc sulfide cloud, salt and sulfide clouds are pretty common.
And nobody has ever seen these clouds only indirectly.
Well, you see them in Jupiter. You see them in the gas giants in our solar system. So there's total like reason to have these things here.
And the things you have to assign like some thickness and density and covering fraction.
We can solve for all of that, yeah.
And you include all those, and
Yeah.
but your forward modeling wouldn't do any of that somehow.
The forward modeling would give you you'd have to actually ask the forward modeler if they didn't already have it to do it for you. So this is this terrible game that ends up getting played because they
It's
could.
like too high dimensional to.
Yeah.
And you've also let the pressure and temperature, some pressure temperature profile is varying here.
Yes.
So you have a flexible temperature, and you're also allowing the abundances of the different,
Gases.
and you're doing that at the molecular level or the atomic level?
The molecular level.
Right.
You can't do it. Yeah.
Because you're not solving like a self-consistent set of chemical
That's right.
equations,
It's
right?
not self-consistent.
Right. Okay.
Right. You can
Yeah,
break
got it.
physics pretty easily.
Got it. Yeah.
Do you have a question?
Exactly.
Are you sure? Because this is just.
Yeah,
I don't even know I'm gonna get through it.
This is just making me talk.
Giving up at the end of the talk anyway. Just jump right in. It doesn't matter. Well, this is what we got for Gliese 229b. So, famous first brown dwarf, super heavy. We tested a suite of models. We've tried to get better about not trying to throw a kitchen sink at it. So you can throw a kitchen sink at everything you can possibly think of that could exist. We tried spinel. We definitely tried hematite. Zinc sulfide was very popular for a while. We're like, yeah, because we went to the like microphysicists and they were like, it's totally gonna happen. You will get zinc sulfide clouds. But it wasn't the best fit model. Overall, we tested them all, no clouds. Cloudless came out fine for this. At least it was the best fit model. We did constrain water, CO, methane, ammonia, sodium, and potassium in the model. And here's the problem of what happened. We ended up with a C to O ratio. For the star, it's a little high, it's an M dwarf. It is a little bit higher than solar, but we got some like super high value for Gliese 229b. And remember what I said, high values mean you form in a disk. So we were like, okay, that's
So Gliese 229b is a planet.
no.
That wasn't the title of your paper.
Absolutely not. What we were like, no, that's definitely wrong. There's right, wrong, and then there's like wrong. And like, this is right, wrong. So this is why this is right, wrong. Because what we figured out was that the problem, if you actually compare the amount of oxygen that we pull out from the abundances, the oxygen is the problem. The carbon basically matches, but the oxygen does not. And I think the reason is, I'll give you the reason in a second.
When you say it doesn't match, you just mean because, so the carbon is different by like 0.1, whereas the in log, whereas the
Yeah, so
air difference by 0.2.
they're
or
basically,
0.3.
it's basically consistent carbon with an error
Okay.
and
fair enough.
significantly different oxygen. So that was a clue, like, where does the oxygen go? And so then we were like, all right, well, let's just compare to all the other retrievals that have been done for companions. So that was the next thing we did. We pulled out all of the retrieved companions thus far to see if this was a common problem. And we did notice that there's a couple of systems where they're totally consistent with each other. So you'd be like, okay, great, you've got stellar binary basically here. But there are other systems that exist where the C to O ratio does differ, and then some that it's just high. And so we're like, actually, I don't think we've learned anything from this plot, except that I think we need more systems. So we turned to every other brown dwarf that anyone had ever tried to do a retrieval on. And this is very recent work over the past like 2 years. And no one had pulled this plot together, but we discovered the following. This is the C to O ratio versus the temperature of the object for everything in the literature that's a brown dwarf that has had a technique called the retrieval technique, which is the only one that can actually do this, performed on it. And the dashed line shows you solar, and it's a massive amount of scatter.
Sorry, and you mean these includes all isolated brown dwarfs too?
Yeah, so
Okay.
everything in green on this plot is a companion, and everything in blue is an isolated object.
Right, okay.
So this would say to you, okay, this institution IB is on the high side, but everything's on the high side. So here's our insight. For all of them, the problem we're surmising is not with the carbon. The problem's with the oxygen. And where does the oxygen go? The oxygen is actually found in the clouds. And so the theory that we have now, which I have lots of reasons to tell you why I think this is right, although it's probably wrong too, is that we don't understand clouds. You don't understand clouds. We know this is a major problem. So part 2 of this is for me to tell you about the clouds. That plot was not to say to you, we figured out formation. We know that all the brown dwarfs form in disks and then get ejected, and that's why they're isolated, because that's an argument that people have made. No, that's a bad argument. So part 2 is there enough information in the observables to confirm the presence of clouds and to determine the cloud composition and the weather pattern? And now I get to show you some of the cool stuff.
I hate to interrupt you again, but are you going to explain how this is true, but also cloudless was your best fit model?
I don't think it was supposed to. I think cloudless was the best model. I think we don't understand. There's a species. So this is the spoiler on that, because that's a T-dwarf, which are thought to be cloudless. We think there might be a mystery absorber in there that we have not accounted for.
Okay.
That's totally possible, and that's where Shannon Vischer comes in, the chemist. He's working with us to try and figure out what happened. Because the other thing that's possible is that it's total disequilibrium chemistry, and that you're wafting up from lower layers, deeper, hotter layers that can have some of those oxygen species in there that sequester the oxygen. That's another possibility that we've drummed up. But the idea is that because the carbon stays solid and there's not carbon in the clouds, the oxygen's in the clouds. These are the examples. I welcome everybody to come visit us at the American Museum of Natural History and see the Hall of Gems and Minerals. When you walk in, you will be welcomed by an entire case of the kinds of clouds that exist on these objects. Here is an entire case of quartz. Gorgeous quartz, SiO2. SiO2, 2 oxygens. There are 2 oxygens locked up in quartz. Yeah. What we got? Give it to me. Did your hand up?
Oh, this is physical theory.
Oh. You asked so many questions, I just assumed. All right. So this is the quartz case. We have a whole other case here, another whole silicates case, and in here we have phosphorate, and we have hematite. Hematite's not the greatest one to think about because we didn't publish it. And statite. All of them have oxygen in them, and these are all clouds that we know exist on giant objects like our outer solar system planets, and I've always been theorized to have in these brown dwarfs, but you have to actually find them. You need signatures of them. So here's the observational signatures that you have these clouds present. This is a spectral type, temperature but not great temperature, versus near infrared color, of a compilation of all spectrally confirmed brown dwarfs, sometimes we call them ultra-cool dwarfs, and you see them get real red and then real blue. And the reason they get real red is because it's theorized that they get this increase in these silicate heavy clouds, these condensate clouds. And then at a certain temperature, those clouds sink below the photosphere where you can actually see them. And instead, something like methane gas comes in and starts to dominate the photosphere. And that's what you start seeing. Now, here's a spectral library of brown dwarfs. And I'm going to zoom in. So these are the M types. This is why these are not black bodies. It's just molecules, zoos of molecules all over the place. You get hydrides and oxides in the higher temperature ones. But there is a feature that I'm now going to focus on for you. That's here in a JWST winning area of the spectrum, right around 7 to 11 microns or so. And I can zoom in on it. This was discovered in 2008 that it existed, and this is the absorption signature of silicon that is in the spectra. I didn't say what kind of silicon it was. I didn't tell you it was quartz or enstatite or phosphorite. I just told you it's just there. It's not in all objects. Here's an example. This is one where it has none. So that bend in the spectrum, the way that it bends, that is the signature of silicon. The debris disk community knows this very well. Anybody that studies great, maybe even interstellar medium folks are very familiar with the signature of silicon that can exist in your spectra. All right, the objects I want to tell you about now. Oh, this is amazing work done by a postdoc in my group. For years, people knew that the silicate feature was an indication of what the clouds were doing. And here's a plot of spectral type versus the strength of that silicate index, and shows you that just like I was just showing you with the colors, where they got redder and then they swept down to bluer, these objects have a strengthening in that silicate feature. It gets deeper, it gets stronger, and then it fades out. And that idea is that the clouds get stronger, maybe thicker, maybe higher, and then they clear out and go below the photosphere. So we did a retrieval of 2 objects because we were really excited about this. We did a retrieval of these 2 objects. Simple 136 and 2139 are their names. In brown dwarf lingo, they're super famous. Super famous. I mean, this is like celebrity status. You know what I'm saying? Like, I don't know, Ryan Gosling and like Ryan Reynolds or Angelina Jolie and somebody else. I don't know what anybody knows. Selena Gomez. Sure. All right, that's these 2 objects, super famous, but they were independent of each other until 2 years ago, where we discovered that both of them were in a 200 million year moving group. So they had the same age. Both of them are T-type objects, which means they're pretty cold. That's what that means. Both of them, because we nailed their age, we could get an idea of their mass, and they are borderline objects, 10 to 20 Jupiter mass objects. That is pretty darn low mass to be isolated and in the field, and no host star with you. If they had been found around a star and directly imaged, this would have been celebration across the waves of the planetary community from the direct imaging side, because they're constantly hunting for these kinds of objects. We find them isolated, much easier to study. All right, now the case of these is that they are T-type objects closer to the L's, which means we can test for different clouds. And that's exactly what we did. So we have more data on these objects. So here's
By
the
the way,
spectra.
just back there, you have the rotation period.
Yes.
Are these in any way close to breakup? Those look like very short rotation
No,
periods.
they're not, but it's a great question. They're very low mass objects, and they it does seem like they're rotating very fast, but this is pretty standard for brown dwarfs.
Okay.
They are very rapid
I
rotators.
see.
But it is important for you to notice that they're equator on. I'm going to come back to this.
What does equator on mean?
The
That means
angle
they're
that
like
you're
this?
viewing them.
Right, but is equator on like this? Or-
Yes.
okay.
Not, we're staring at the equator, not at the pole.
Okay. Got it.
Yeah. This will be important in a second.
Oh, otherwise you would know the rotation. Okay, yes.
Well, you could, because there could have some variability at the pole. You'll see that in a second too.
Okay, I'll let you know.
Okay, almost there. I know. I'm gonna run through the JWST data, but I just want to get through this really great point. It's a discovery we've just made in brown dwarf science, and I'm so proud that we got to this point. This is all the work right now being led by a postdoc in my group, Johanna Voss. So we took the data for one of those two very famous brown dwarfs, Simple 136, water, methane, it's got CO in here, more methane, and then it's got the silicate feature, which is exciting to find. So silicate feature is there, and then we compare it to its twin, where we don't have quite as much data. We were missing the 3 to 5 micron data. This is really hard data to come by until JWST. JWST fills this in big time, but before JWST, and this is a pre-JWST target, we didn't have it. But these two objects overlaid is the retrieval. So black here is the data, and green shows you our best retrieval. We threw a kitchen sink at this model-wise. We threw a kitchen sink at this one, and we came up with a best fit model that you see there that fit the silicate feature. And then we threw a kitchen sink at this one, and black is the data, green is the fit. We threw a kitchen sink at this one, and independently, we found that they had the exact same best fit model. And that was a cloudy, patchy phosphorite cloud over an iron deck cloud. So it's complicated because when we have the data that we have on an object like that, we can play with not just one cloud. We can do a double cloud layer, a triple cloud layer, a quadruple cloud layer, adding more whatever model issues that probably make some of that nonsense. But in the case of these two objects that are variable objects, we were able to test and really well constrain the spectra, and then come up with these models, and we constrained water, CO, CO2, methane, ammonia, sodium and potassium, chromium hydride, iron hydride, and silicon oxide. And here's a TP profile, which was, this is what the temperature versus pressure looks like that comes out of our best fit retrieval. We allowed a flexible TP profile, and if we saw it deviate significantly from the green line, the yellow line, the blue line, whatever colors you see here, these 3 lines here, that would be bad, because this is what the self-consistent models tell us should be happening. But it looks good. It looks like it found a TP profile that deviates enough where it's hotter at the top than was expected, but fits well through the photosphere here. And then the dashed lines show you the intersection of a condensate. And that's why we ran into the phosphorite cloud, which you can see where we place it in the atmosphere. This is low pressure, so high in the atmosphere, versus high pressure, low in the atmosphere. And we were able to determine that an iron deck over a patchy phosphorite cloud could really well fit the data.
But this is just saying they could also exist. Like this is saying it's like, it is in some sense physically consistent. Is that the point of that plot?
The point with that is this is the best fit model.
Okay.
And it's telling you that to reproduce the data that we had, take an iron deck cloud, squash it down a bit into the atmosphere, because we think iron deck is pretty classic brown dwarf. The self-consistent models use it all the time.
Okay.
Because chemistry, temperature-wise, this is what's expected to condense out. That's what chemistry tells us.
Okay.
I'm not the chemist here. I'm just going to grab from the chemistry tables and then say, like, okay, this is the temperature and the pressure that we think exists in these sources. And then the phosphorate cloud, but you could have other clouds here too. You could have a zinc sulfide cloud up higher. You could have an enstatite cloud higher, maybe even lower, but none of them fit the data as well as this. And this fit both of them. So that was telling us something, and here's the important thing here. The C to O ratio for these two isolated objects, whereby we were able to do the clouds, we fit the clouds well, came out to near solar, and they matched each other. Does it mean that we found everything? I don't think so, But what this says to me is that I don't think we've found the oxygen absorber in those T-dwarfs. I think there's oxygen getting sequestered and we're not finding it and figuring it out. But we're figuring it out for these objects. Because they are matching each other and they are matching what we think. This isn't perfect. I'll just fly through this. It's not perfect. Water doesn't match between them. Neither does the CO. And that's what ends up driving them to have slightly different metallicities. But we have a theory about that too. One of them is an auroral emitter. So it has aurora. It's been detected in the radio. And so it's got a really beautiful auroral signature. The other one has been looked and it does not. And we think there might be some photoionization happening in the atmosphere that's doing something to the hydrogen. The theory. All right. This is so good. What we're able to then back out of that retrieval is say, if that's the cloud scenario, if it is a pachyphosphorite cloud over an iron deck cloud, and it looked really good, what is your prediction for where we would see variability of the object? And the prediction is that you would see variability in an HST filter here. And in fact, people have monitored this object in HST, and we do match their variability prediction. And then you would have variability in Spitzer 3.6 and 4.5 microns. This is the amplitude prediction, and the black shows the actual data from HST. The blue shows our predicted variability, and we nailed it. We got the HST variability correct, and we predicted the Spitzer variability amplitudes, and then we predict that if you were to stare at this thing with JWST, in MIRI Channel 2, this is a big deal for making proposals. A lot of people want to try this, and they're basically fishing for reasons to go after this. This gives you your prediction. You're going to find an amplitude of variability in that silicate feature that's probably going to be comparable to what you saw in the Spitzer monitoring. All right, the last thing I'm going to tell you about, I'll show you the JWST spectra super quick, but I want to finalize clouds for you. This is what we think the visual is of what's happening. You have a rapidly spinning brown dwarf. You have a light curve that's changing. This is how we can check the changing photometry. You get holes that are leaking out hotter gas from deeper down. This is not so dissimilar to watching the 5-micron hotspot on Jupiter as it goes around. We do see this on Jupiter, literally analogous to what we see in the gas giant.
Why is it not periodic strictly?
Because look at those cloud patterns. I mean, they're I think what you're probably focused on, and this is also an animation, so it's not perfect, is the translation of the animation to the light curve. And I actually think that's the physical light curve that they had from Spitzer.
So you're saying cloud variability timescale is comparable to rotation period, or?
You can so you're probably focusing on the complicated look of the light curve, but what you look at is the trough to trough and try and back away from the multiple sunspots that you might be seeing. They're cloud holes.
No, I'm just, because if you look at the sun, for example, the time variability timescale for sunspots is much longer than rotation period of the sun, right? So it will be, well, comparable, but still. So here you are saying the clouds are changing very quickly.
Very quickly, yes. We see their morphology.
Even within 1 day or whatever.
They can. The rotation period is 2.5 hours.
Think about the Earth, right?
Yeah. Yeah.
Yeah, maybe you're right.
Yeah. So this is just to say I had a 600 hour Spitzer program to monitor brown dwarfs to see how they vary. And I went after young ones because young ones we think are, well, we concluded young ones are far more variable than older ones. So great. But that left us with one unanswered question. And this goes back to what you were asking. Are you looking at the equatoron or polon? So you don't know what you're looking at, actually. You are just staring out into space, and we're all at some weird orientation to each other. There's no reason to think everything is going to be equator on. It could be polon. And these are images from Juno, from the mission that's orbiting Jupiter right now, and this is what Jupiter looks like equator on, and this is what Jupiter looks pole on. And if you're going to try and draw the same conclusion, you better know what inclination angle you're looking at.
Is that the same, filters and all of that? It's just
Yeah.
amazing.
Yeah, and look how different the cloud structures are. So we asked the
You
question.
can also see that you see through the limb differently than you see through the,
Yeah,
like it's really totally different.
totally different. So this is a new result that we have, and the only way this plot I'm about to show you is possible is if you have dedicated a massive amount of time and a career to studying these objects. And I'm talking about the whole brown dwarf community, a large component of the brown dwarf community. Because you want to be able to figure out the inclination angle. What angle are you at? In order to do that, you have to have a rotation. You have to see that the object is variable, so you have to be able to measure the rotation. So you have to basically have some sort of variation. You have to have a V sin I value. You have to have a high resolution spectrum. Combine the V sin I with the rotation rate, you can get the inclination. Those are hard measurements. And then you have to have a mid-infrared spectrum. And really, all you have to look at is Spitzer's IRS, which only lived for a short period of time. So we asked the question, what does inclination angle tell you about the cloud features? And we found the following. So here's one that's nearly pole on, and it did have a measurable but very small silicate index. It's also variable, so we could detect some variability. Not totally pole on though. And you can see its inclination angle with a really small silicate index. On the opposite end, here's another one with a very strong silicate index and nearly equator on. And our discovery was that it matches. And I'll just tell you, in brown dwarf science, you never get to see a trend. Ever. Ever. I'm not kidding, ever. And this just lined up. And also we color coded it by the near infrared color, which in the early days of brown dwarf science was the attempt to predict the cloud properties. And that lines up well too. So basically, inclination angle is a critical parameter if you're going to try and figure out your clouds. So, all right. That's basically all the time I have. I'm not going to show you the JWST data unless you really want to see it.
Obviously, we want to see it.
All right, fine. JWST data, I'll go through it really quick. And this is from a planetarium presentation that I did the other day. I invite you all to come visit AMNH if you haven't. You really should. It's really fun. And
This is Jackie's Viz setup.
Well, this is also where the Big Apple Colloquium is.
Yes!
December 8th, that
So-
Jackie's organizing.
Yeah, so the Big Apple Colloquium, which will have Heidi Hamill talking about JWST, is going to be inside of the dome. We're going to be flying the data so that you'll be able to see where the telescope is, and you're going to be seeing images and where they pointed the sky. It's really fun. All right. So I have a JWST program. Here's some JWST data. I'm on this paper, but I did not lead this paper. Brittany Miles led it. This was the early release science data. And this is a brown dwarf planet. This is one of these objects that bangs on the door of the question, are you a brown dwarf or are you a planet? So everybody wants to go after this thing. You can zoom right on in and see very clearly at a better resolution than we had, a really strong signature of that silicate cloud, that silicate feature. Never before seen, very, very exciting. We are trying really hard to do the retrieval to back out the chemistry, and my new postdoc, Mal Whiteford, is in charge of this for the ERS, but it's hard. We haven't figured out how to handle JWST data yet. It's higher resolution, it's more data. We have to right now de-resolve the data to Spitzer resolution in order to do it. I know. It's fine.
It was only $10 billion.
It's fine. We will figure it out. But at this point, we haven't figured it out. And it could be calibration problems, but it could also be because with this resolution, a computationally expensive thing. It usually takes us 4 days a model to get to a retrieval. And I said we threw a kitchen sink at it, which means we tried like 25 to 30 models, and you had to run them and then rerun them and then run them and then rerun them. So those that are familiar with this know that is a pain in the rear to be doing that. And this instead would take like 12 days to run. So we're not there yet. We'll figure it out. We're figuring it out. All right. But here's what I'll show you, my brand new out of the box data. And it's going to be on cold world. So now I'm going to take you all the way to the opposite end of the classes of objects, the coldest objects. Remember I made a big deal about the 250 degree Kelvin thing? So I'm going to show you how we don't know anything about diversity because of what we're finding in this data set. All right, so this is how I chose the objects for the program that I led. And this is going to be a Spitzer color. Spitzer's channel 1 minus channel 2. The warm mission of Spitzer was just our bread and butter in brown dwarf science versus the absolute magnitude in 4.5 in channel 2. The other thing I will tell you about this plot is this took so much time and energy because it's going to be filled with objects which we painstakingly measured the parallaxes for. Gaia is so great, but Gaia cannot reach these faint objects. We had to beg and scrape at photons from Spitzer because these things are so stinking faint. Here's what we had, which is it's crazy what you're seeing. So and the reason it's crazy is because of how much diversity you find in a given color. So as you go from left to right, you're going from warmer objects to cooler objects. And this guy here, notice this big gap? That's embarrassing, but what's happened is we have no idea if there's really no other object like it. Did we work really hard? We haven't found them. What's the deal? This is the 250 degree Kelvin object. So what I did is I said, all right, we don't understand anything about these objects until we get spectra. So I binned this diagram into 4 parts, and I selected these objects in black, 1, 2, 3, in 4 different bins. And I said, I'm going to pretend like I could form a line through what I'm going to call the median, and I'm going to call those objects normal, and then I'm going to figure out what the heck's going on with the bright thing and the faint thing. Bright thing and the faint thing in one. All we had were these wavelengths. We had no other wavelength because they were too faint. We couldn't do them from the ground. We couldn't do them from anywhere. And the hope was that we would see something crazy. And here's the JWST data. This is the first object. This is the warmest one. In black is the data, and in blue is the model. And what I can't believe is that the model fits anything. And it's not perfect, but this whole like little serenade that's happening here is all CO. This is like a massive amount of CO. So this was supposed to be our warmest object, and then this one was supposed to be one of our coldest. But if I blink them, look at the CO. Oh, that's a different one. So what I don't understand, this CO feature, which appears to be very temperature sensitive, is turning out to look the stinking same between those two. But 1935, this one, which we had said, we tried really hard on other telescopes to get data on this, and nothing. All of a sudden it shows up like the same as this object, which we were able to get this from the ground. This is our brightest stinking object. And then here's one of our colder ones, and you can see how different these two are. So every line that you see in here, every one of those line wiggles that are up, down, up, down, up, down, that's a new now pathway to understanding the chemistry of what's happening here. We're going to model all of this. We're going to get to the clouds because this is telling us where the oxygen is. There's a lot of oxygen related features in here. And we're going to dig deep, solve this clouds problem, and these are the coldest compact objects. So, all right, that's it. My conclusions, number 1, chemistry. If you hear anyone say you're going to learn a lot about formation from the C to O ratio, ask them about the clouds. then say, did you figure out your clouds yet? And if they say clouds aren't important, tell them to come talk to me. And then part 2, clouds. You get the mid-infrared data, you can constrain those cloud properties. We got a lot of signatures of it, but you have to be warned. Young objects are more variable, and that inclination angle impacts your result. And then part 3 is like diversity. It's going to be a ton. You're going to see a ton of this come out with JWST for Jupiter-like objects. I just don't think we understand objects that are at the temperatures of Jupiter at all. Okay, that's it. I'm done. This is the rest of my
So
research.
we had many questions, so if you feel like you need to go now, feel free. But I think we're gonna keep Jackie here if there are more questions.
Yeah, if anybody has any more questions. Yeah.
So, can you show this picture of Jupiter with aurora?
Oh, the
Yeah, where
inclination
you
angle
compare
plot.
the equator on and pole on.
These guys.
Yeah, so is the, and I think Gladys asked, and you said this is a real picture, no fooling around with it. Is the aurora actually as bright?
Oh, so I shouldn't have said no fooling around. I don't know what they do completely to enhance the pictures. Like this does.
So this looks too good to be
Yeah. What I mean is like you can tell.
Yeah,
I'm
this
looking at the
I
cloud bands. I wasn't looking.
But it's not a true picture, no.
But it is a picture. Yeah.
Picture.
It's just been color enhanced a little
Right,
bit.
right, that's what I'm saying. Like Galileo, when he was looking, he didn't see this bright aurora.
Yeah.
Couldn't see the infrared.
No, that is. I don't know what
Aurora
wavelength
is
the
blue
aurora.
probably, no?
No, yeah. You
Well, it
can.
could be
Depends on what
HL.
you're looking at. If that's OH or something.
Yeah,
Or it could be some line.
Yeah,
or something.
Depends on what filters they use, because these are color created.
And also another question, why don't you have aurora on the South Pole?
Jupiter has a pole issue, and the aurora of Jupiter come from Io. So Io yields this
But still
plasma.
Io is in the equatorial plane, I would think.
Yeah, I don't know that they've seen the aurora on both poles. I think that they have, because it could be I don't know where Juno also was when it took this
Okay.
full-on image.
And the last one, so you kept saying throughout your talk, is it a brown dwarf or a planet? So
Yeah.
you must have a definition. Did I get it right? That it is the CO ratio or something?
So my
You
conclusion
never
on this.
stated the definition for us.
Right, and there's a reason, because we don't have one. And that what I was
But if you
suggesting.
don't have one, how can you ask a question, is it a planet or a...
Well,
Like to ask, for example,
I
is
understand
square
what
root
you're
of 2 a real number?
well, listen. Here's the thing. I don't think that there is a definition. I do not believe that there's a good way to classify these
Then why are
objects.
you asking is something a planet or a brown?
What I want to know is the formation mechanism of an object. And what I was
Unless you are
suggesting.
doing humanities,
no,
you
listen
should
to
have
her
a
answer.
definition.
No, listen, this is really important because people fight over classification schemes. They fight over, should I call this, and I don't know what there's a lot of cosmology in here.
Galaxies. We argue is a galaxy.
Then is it
Or
a
is it a-
galaxy or not? A dwarf
Yeah.
galaxy or a globular cluster? Maybe go with that or something, I don't know, whatever. We cannot, what I'm gonna say to you is that it is a very interesting question to ask. Is there an object that you can definitively say that's a planet? Or is that just a stupid question to ask? And you should just study everything as a spectrum.
Well, a
That's what-
related question, what about the population of brown dwarfs? You showed us some cases where they might be in a companion with a star.
Yeah.
You might have said, well, okay, if something has a lot of brothers and sisters that are clearly planets, then we might. So, do you
Yeah.
ever find things that are brown dwarf-like with other planets? I mean, tell
Yeah,
us a little about that whole question.
We do. I mean, this is this plot. Oh, I have another one for you, but I don't have it up here. Yes, for instance, I could look at here's another area of science that I think can help get at this. You can look at a moving group, a cluster. Think of it like an open cluster. So go to an open cluster and you say, okay, I've found stars that have a really tight companion, and then one that's a little further, and then I found another star where it's a little bit further, and then I found one that's isolated and all on its own. And each one of those objects are the same temperature, and they all form together because they're all from the same natal environment. So therein, you want to ask the question, okay, I'm going to look at just those objects then. Same temperature, they would have come from the same metallicity because they came from the same natal cloud. Is there any difference between them? And that's a question that I am asking in a JWST Cycle 2 proposal that I'm planning on putting in, because that is a sample we could look at. I still don't think that we're going to get to an answer because I think that there's a complex, I don't know if there is going to be a smoking gun that's going to tell you, where you're going to be able to say, that one definitely formed in a disk, and that's what we want to use as the planet formation take. Because that is the definition I want. Form in a disk, I'll call you a planet.
Don't binary stars form in a disk?
I don't think that they form in disks around each other. They form out of the same fragmented piece of a cloud, but you have to accrete material in a cloud that doesn't have, in a disk that doesn't have much material, which is why you usually see the mass ratio really low, because you don't form a 70 Jupiter mass thing around an 80 Jupiter mass host star, where all of the material for the 70 Jupiter mass thing came from the debris disk around the 80 Jupiter mass
So this
thing.
cloud disk separation is probably the definition.
Well,
That's all there is. As far as you're kind of saying, that's all there is.
that's what we
I mean,
have.
Could we rephrase the questions that people are asking in low mass objects without ever making the planet star distinction? Like, what, you know, it's kind of important to astronomers to have these like categorizations. Like, I'm an exoplanet astronomer, I'm a stellar astronomer, but it's not obvious that we need it. Like, it's not critical to most of those papers about those exoplanets that they have been formed in a particular way.
I think that there's science in understanding a formation mechanism,
For sure.
and there's also science in understanding what the basement of the star formation process is. And that is something that we try to go after, but you can't go after it if you start over counting the low mass end of things, because you have ejected planets. It is a thing. I do think you have ejected planets. I do think that they're out there. We have a paper I worked on where we clearly saw planet-planet scattering that very clearly ejected something, in that there's a dynamic signature of the ejection there. And what would it eject? Something a little bit smaller, and so it was going to be like a 5 to 7 Jupiter mass object, which is basically the kind of object I was showing you the JWST data on. So you can eject them, but then if you find them isolated in the field and you overcount them, you just miscalculated star formation frequency. You don't know what the initial mass function is, and you don't know how to compare, because don't you want to go in cosmology and like look at the star formation rate and like look at the full
I
formation?
prefer we not count any of these stars in the star formation rate.
Why?
I think it's a mistake to count them, because we can't predict how many form, and we can't measure how many form or how many are forming. It's everything below like half a solar mass isn't observable cosmologically.
Yeah,
So
well,
we should just cut it off there.
No,
But anyway, you
so every single
You don't
round,
really get to decide.
the universe eventually will just be filled with ground words anyway. Also,
It'll be the only thing left to count.
nobody asked me like how many brown dwarfs are there, like how many brown dwarfs versus stars. And at the beginning, when they were first theorized, they were originally theorized to be the dark matter, the component of the dark matter halo. Like we didn't know where they were. We thought that there were 20 times more brown dwarfs than stars. And then once we started to study the mass function, we learned, maybe not. There's one brown dwarf for maybe every 5 or 6 stars. So they're way different than what the original thought was. They are a major constituent of the galaxy, but they aren't the dominant constituent like M dwarfs are, for instance. Mid-type M dwarfs are the peak of the mass function. They show up in number more than anything else does.
When people, how much is done in comparison with the solar system planets? So, you know, a lot of the things you're saying could be applied to Jupiter directly.
Yeah.
And of course, it's very different to observe Jupiter than to observe, but have people tried to build like the spectrum you would have observed for Jupiter if it was a single point source very far away, and then asked if they try to do your kind of retrievals, whether they get the right answer? I mean, Jupiter is in a different box, but
I
I'm
believe
still.
they did that experiment in the 1970s.
Yeah, so
And
No, no, I mean, they observed Jupiter.
Well,
as
no,
a
they
point
did,
source.
that's like a dot, yeah, exactly.
Well, so what the problem is with something like Jupiter is that all the data that we have on it, the spectra that you have on it, that you want to overlay on top of this brown dwarf stuff, which we have done, and we have compared, and you can see interesting differences, is that Jupiter is reflecting light from the sun. So you need to get it on the dark side. And so, dark side is always the wrong word. You need to go see it on its night side and then take a spectrum of it when it's there. And there was arguments to get Voyager to do it because, I mean, it's weird. It's like, can you go over to where there's no light and take a spectrum for us so that we can compare it to our brown dwarfs? Like, this was arguments that were made by several of the modelers that wanted to check on their data, and they did get some data. Voyager did give an integrated light spectrum that we do use to compare. It would be great to have more data though, and be able to compare and contrast, because Jupiter is exactly analogous to these objects. So we went way over.
Yeah,
You guys are being
well,
very
yeah,
kind. to ask
people are
me
wandering
questions.
off, but
Yeah.
let's thank Jackie again.
Oh,
I'll stop it for that.
yeah, okay.